Hello, mathematicians. Today we are on one of my absolute favorite sections. Probably my favorite section over chain rule is applied optimization, section 4.6. I love this section. It was my favorite when I was learning calculus. It is my favorite to teach. Maybe that's why I study applied mathematics. So hopefully you guys will find this fun and interesting because it's a little bit more problems relevant to what can be real, like what calculus can really be used in the real world. Basically, optimization problems or applied optimization problems are going to be like, given this much wire fencing, what's the biggest area I can make for all my cows? Is it, and I want it to be a square or a triangle or a circle, something like that. You're going to be given a lot of information, a lot of numbers, and you're going to have to be able to digest all of that and figure out what to do with it. After a while, after a few problems, it'll kind of become a little bit second nature, but there's lots of different problems, just like there were for related rates. Lots of different equations that we kind of need to pull out of our brains, like surface area and volume, perimeter, area of like cubes, spheres, pyramids, cylinders, and then a combination of all of those. So it might seem very scary, but it's really, really fun. And I promise you, you'll do great. Okay? So first, before we get into optimization problems, we kind of already talked about like what they could be. You can maximize profit, minimize cost. If I tell you how much it is to cover something in wrapping paper so many times, you want to minimize that cost. I want to maximize the amount of area that I can get out of this single fencing, stuff like that. When I took calculus, we had this really fun project, because I think it was around, I don't know when, we had a party and we had to make, it had to be like math related. So we optimized like how much icing could go on a cake if I had that much, like what shape it could be, and we had to like show the problem and then like bring in our treat. It was really fun. But the difference between related rates and optimization is usually you're given two equations, one you're optimizing, like say area or surface area, and one that's kind of set in stone, like perimeter or volume. It could always be switched though. So sometimes you might even have equations that you need to use area or volume and to build something that you're optimizing, and we'll get to problems like that later. So I've written down kind of a good way to solve applied optimization problems, and so let's run through those now. So read the entire problem, which seems like duh, but you need to ask like, what am I given? So like when I read optimization problems, the first thing I was like given, and then I write like area equals this, or I know that it's supposed to be this shape or something like this. What quantity is unknown and being optimized? If I'm asking for the maximum area, the minimum cost, is it asking for the dimension? Like what is it asking for? What do I need to know once I've done all this math? What do I need to give as an answer? All right, then draw a picture. Pictures are so helpful. Bailey and I, when we first started our first year, I like was not getting homework problems and I just didn't understand, and because I would just sit and look at the problem and then be sad that I didn't understand the answer. And Bailey was like, just draw a picture. And then it'll amaze you how much better it is to actually do math on paper instead of just trying to do everything in your head. Please write things down. Please draw pictures. They can only help you. And then label them with what you know. If I draw a box, I'm going to label the length, width, and height by what information I know from the problem that was given to me. All right. So 3, we're going to introduce variables. So we're going to list the relation between variables, right? I know some areas, I know perimeters, surface areas, volume. I know those. Sometimes I'm also given that something is twice as expensive as something else, or 3 times expensive as something else, right? You might sometimes have to create these equations. I'm getting out of breath, I'm so excited. So 4, we're going to write an equation for the optimized variable. The optimized variable is also the one that we don't know. We're trying to figure out what that is. Usually we're given two equations, and I have lots of different variables. I use that one equation that, let's say I have the number of wire is 800 meters. So I know the perimeter needs to be 800 meters. And I can use whatever the perimeter of my like shape is, that's going to equal 800. So that's going to help me get a variable in terms of another variable. So then I have this one optimization problem with just one variable, and I'm not taking the derivative with all these different variables because we don't know how to do that yet. All right, so once I have this problem that I need to optimize, I'm trying to find a max and a min. Well, we do that by testing our critical points and our endpoints. So we're going to use either the first or second derivative test, kind of whatever you want to do, which one you find is best. The endpoints, we're also going to test our endpoints, obviously, because those can be max and mins as well. Endpoints can be found when considering the real-world application. This first problem we're going to go to, we're going to be cutting a piece of paper, and there's only so much paper we can cut, and I can't cut negative paper. So you kind of have to think about, do negative values exist in this situation? Remember, distance, we can't have a negative distance, but when I'm cutting paper, I can't somehow cut and add paper. That'd be really cool, but we can't do that. All right, so now that I'm done like rushing through this, let's go through. I have 4 problems for us to do. That is kind of like a mix of different types of problems and different equations that we can work through and kind of get a better handle of optimization problems. All right, so the first one is we have an open top box, and it's to be made by cutting a small congruent squares. So congruent means the same side, but that's also like a square. From the corners of a 12-inch sheet of 10 and bending up the sides. How large should the squares cut from the corner to be? Did I just copy this word from the textbook and it does not make sense? How large should the squares cut from the corners be to make the box hold as much as possible? Okay, that made more sense. So I've kind of already drawn our 10. So you can see that this dark gray square right here, that is our 12 by 12 sheet. And then I colored in what would be left of after cutting out our little congruent squares. So each square is the same. And then if I fold on these lines, that would give me my open face box. So my pictures really help. And also, like, they're really fun to draw. So you'll see some of my later pictures that are like pretty funny. So what am I given? So we are given that it's a 12 by 12 sheet. So that tells me the surface area of my box. And I want to maximize the volume. So note that volume and surface area go together, and perimeter and area go together if I'm talking about something that's 2D or 3D. All right, so let's call each side of each square X. So let's see, what did I do first? I want to maximize my volume, so I need to make a volume equation. So I know volume of a rectangle is length times width times height. So the length and width of my box is actually, the length and width are going to be equal because it's a square bottom. right? And I don't know what my height is, but if I look right here, when I fold these boxes up, the height is going to be X. So if this 10 sheet is 12 inches long and I make one X cut here and one X length cut there, I took, let's see, let's look at our length, which we know equals width. So I'm going to have 12 inches, and then I'm going to cut one X square out and then another X square out. And that'll give me 12 minus 2X. And then my height is going to be X. If I fold this up, oh God, let's see if I can draw this. Wow, honestly, you get an art degree. So that's kind of what our box is going to look like, but we're not going to have a top. So this is going to be X tall and 12 minus 2X wide and long, since it's square. So volume is length times width times height. So I can plug those all in. Oops, not for T. X is time to shine. So I'm going to have length, width is 12 minus 2X, times width, which is 12 minus 2X, times my height, X. And then I can simplify that just to 12 minus 2X squared over X. And if you wanted to FOIL that, absolutely. I don't feel like doing that. So cool. Now we have my equation to optimize. I introduced some variables, length, width, and height. I found some relationships between them from the question. And now I have these equations that I picked, right? Length equals width. I know that I can only choose 12 minus something X or 2X and get those equations like that. So we get this volume equation. We also need to talk about endpoints, like how big X can be and how small X can be. Well, I can just choose to not cut out X at all. X can be 0, and I can just choose to not cut any squares. It wouldn't make a really good box, but it could happen. So the smallest that X can be is 0. What about the biggest? If each side of the 10 is 12 inches long, and I needed to cut 2 squares, the largest that I can cut is going to be 6, because I need to be able to cut 2 squares. All right, that would also just cut the paper into like 4 different squares, but we still need to test the endpoints anyways, okay? So now we have our endpoints and our equation that we're optimizing volume. So we want maximize volume, and we specifically want what X is. All right, so now we're going to find our critical points. So we're going to take the derivative of our volume. So we get 12 minus 2X times negative 2X times X again, right? So we took the derivative of this function of X and we kept this one, plus 12 minus 2X squared. And then times the derivative of X, which is just 1. Alrighty, so let's simplify this. Each term has a 12 minus 2X. 12 minus 2X. What's that going to be? Negative 4X squared. plus 12 minus 2x. Let me make sure that's right. Why is there a squared? Oh, whoopsies. That x doesn't exist. Okay. Sorry. All right, so then I can simplify. I can pull out a 2 this first term, so I get 6 minus x. And then 12 minus 6x. Pull out 2 out of that one. So I get 4. 6 minus x. What is that? 6 minus... Oh wait, I'm gonna pull a 6 out of here. So that's gonna be 12 2 minus x. Okay. So I pulled a 6 out of here. So that gave me 2 minus x. Okay. Beautiful. So that's what v prime of x is. So now I'm going to set that equal to 0. Which tells me that 6 minus x is 0, or 2 minus x is 0. So either x equals 6 or x equals 2. So here in optimization, we are looking for absolute extrema because we have a closed interval, right? X is between 0 and 6. So I'm lucky enough here that x equals 6 is actually my endpoint. So if I plug in 6, 2, and 0 into my volume, whichever one gives me my biggest volume is going to be my absolute max, which I want. So we'll do v of 0. Remember, v is 12 minus 2x squared times x, so that's going to be 0. V of 2 will give me 2 times 2 is 4, so 12 minus 4 is 8. So we're going to get 64 times 2, which is 128. And then v of 6 is 12 minus 12, 0 times 6 equals 0. Alrighty, so I think it's pretty clear that 128 is larger than 0. But to finish it out, we would say to maximize the volume, two-inch squares should be cut out, right? And we also want to add on a unit. I forgot the word for that word. We want to add a unit, right? We were given units in the beginning. We had a 12-inch by 12-inch. So this is a pretty common optimization problem. I was taught this exact problem when I took calculus. So a pretty great one. And then it would be, I could even go back and ask if I told you that I wanted to minimize cost, something like that, and I give you, but it needs to be this volume. That's another way to have the same problem, but just like different things that need to go on with it. Alrighty? So next problem. So, I know guys, my drawing is getting so good. So we're given that a rectangle is inscribed in a semicircle of radius 2. So this is like 1, this one's 2. So then, what is the largest area the rectangle can have, and what are its dimensions? So, we have our semicircle, or radius 2. Can I write through this? Okay. Whoopsies. So we're given semicircle, radius 2. I can make an equation for that. And the rectangle needs to be inside of that. So the distance from here to here also needs to be 2. So if we call this x, then this would be negative x, because this is negative 2. Then this point on the circle is going to be x, and then whatever the equation for the circle is. So it might be some time since you guys had to know the equation for a circle. So a circle is x squared plus y squared equals the radius squared. In this case, our circle is going to equal, the radius is 2, so it's going to equal 4. So this is just a semicircle. It's only the positive half. So I can take x squared plus y squared equal to 4 and solve for y. So that's going to give us x squared plus y squared equal to 4. So then y squared equal to 4 minus x squared. And then we take the square root. And we only want the positive one because we're like the northern hemisphere. So I only want the positive square root. All right? So that means that this little guy's y is going to be 4 minus x squared. Okay? So if this length is x, the height would be 4 minus x squared. Okay? So we want the max area of the rectangle. So, oopsies. The area of the rectangle is going to equal length times width. Our length in this case is, well, if the middle of the rectangle is at 0, it's going to go x to this side and x to this side. So length is going to be 2x, and its width, I think I called it height earlier, is going to be its y value, square root of 4 minus x squared. So if I make, let's make height like, so if I made my width green and my length red, okay? I hope that helps. So now we have an equation for area. And actually it happened so enough that I only have x's again. which is awesome. I only have one variable. So before we take the derivative and set it equal to 0, we need to look at our area and figure out what the maximum x can be and the minimum. So the minimum here is, and usually is, I'm not gonna say it always is because that's a very strong statement. I can't make x smaller than 0, right? If I make it a negative number, well, negative x is still going to go onto the other side. It would kind of be like a little redundant to make it negative. And the biggest that 2 can be, just by looking at the square root right here, the largest that it can be without putting a negative under that radical is 2. Okay? Also, it's inscribed in this semicircle, so I can't go past. X can't be larger than 2. Alrighty. So now we have, okay, that our area with respect to x is 2x square root of 4 minus x squared. Alrighty. So, get my bearings. Now we're going to take the derivative. So a prime, okay, give myself a whole other page, great, of x equals, so let's take the derivative of 2x, so it'll be 2, 4 minus x squared, plus 2x, 1, oops, 1 divided by 2 square root 4 minus x squared. That was the derivative of the outside with the inside still the same, times the derivative of the inside. So the derivative of 4 minus x squared is going to be negative 2x. Going to simplify. So I have 2 square root of 4 minus x squared. Minus, let's see, one of these 2's is going to cancel out. Minus 2x over the square root of 4 minus x squared. All right, cool. So I need to find my critical points. Critical points are when the derivative equals 0 or is undefined. So notice that undefined means when I am dividing by 0 at any point in my equation. So a prime of x is undefined when the square root of 4 minus x squared is equal to 0. So then that means when 4 minus x squared is equal to 0, and x equals plus or minus 2. But remember, x is only has to be greater than 0. So we don't need that negative. It's basically kind of the same as saying plus 2. So one critical point, x equals 2. So now we're going to set our derivative equal to 0. So we have 0 equal to 2 root 4 minus x squared minus 2x square root of 4 minus x squared. Going to add this big fraction to the other side because it's negative. So I'll have 2x over 4 minus x squared, woo, equal to 2 times. So now I'm going to multiply each side by 4 minus x squared. Or, sorry, root 4 minus x squared. So that'll cancel out these guys. So I'm left with 2x equals 2. So the square root of 4 minus x squared times the square root of 4 minus x squared is just going to be 4 minus x squared. All right, I'm going to divide by 2. So I get that x is equal to 4 minus x squared. Subtract that x over. So 4 minus x squared. There's something that I missed. Oop, that was squared from all that time ago. Haha. Okay. Whee. Okay. So then I'll get, if I add x squared to both sides, we get 2x squared equal to 4, x squared equal to 2, and x is equal to plus or minus the square root of 2. But as we said before, x can only be positive here, so we're going to keep square root of 2. Square root of 2, I think, is like 1.5 something, 373. So now we have our 2 critical points and our 2 endpoints. One endpoint, and it just happened again that one, where was my other critical point? Oh yeah, x equals 2, and x equals the square root of 2. So now we're going to plug in our critical points. Okay, so the area at 0 is, what is area? Oh, right here. 2x, 4 minus x squared. Right there, over there. Okay, so if I plug in 0, I get 0 times square root of 4. That's just 0. Times the square root of 2 is going to equal 2 root 2 times the square root of 4 minus 2, which is just the square root of 2. So I get 4. Okay. And then if I plug in 2, then I'll get 4 times 0, which is just 0. It's funny how the endpoint just gives me 0. All right. So we can clearly see here that x equals the square root of 2 is what's going to maximize the area. So let's go up here, and we wanted to know the largest area the rectangle can have. So the largest area is 4 units. If you don't know the units, if they're not given, especially when it's kind of something about something on a graph, we're going to go with units as our unit. So the largest area is 4 units when the rectangle is square root of 2 units high and 2 root 2 units long. Alrighty, so those were some pretty, I like these problems, but not too much, because I like problems that, like the next one we're going to do, where you're given two different types of equations. One's kind of set in stone, it's equal to something, and I want to optimize something else, right? So this is my favorite problem of all time, as you can see by my drawing. So we're given that a rectangular plot of farmland will be bounded on one side by a river, which you can see that I've drawn, and on the other three sides by a single strand electric fence. So single strand means just one strand's going over. With 800 meters of wire at your disposal, what is the largest area you can enclose, and what are the dimensions? Kind of going without saying is the way that to get the largest dimension or largest area is to use all 800 wire. So, and that wire is going to go around this rectangular field. So that means that's the perimeter. So we're kind of given that the perimeter is going to be add up to 800 meters. And we want, what else do we want? Max area and its dimensions. So I like to call this side L and this side W. That also makes this side W. It's a rectangle, so I know that two sides have to be the same, right? The opposite sides. I just know that from rectangles. All right, so kind of also given in this problem, we're just looking at the picture. Cow and fish are optional. Look how cute my fish is. So now let's create the equation for length and width. So I know perimeter is going to be 800, but my perimeter isn't going to be 2 times the length, 2 times the width, because I don't have all of that. I'm missing one of my sides. So if I just add them all up, I have 2W plus L. Well, I know that needs to equal 800. All right, and I want to maximize my area. Well, the area of a rectangle, even though it is missing that side, ignore the squiggles of water. We're acting like that's straight. So area of a rectangle is just length times width. Well, so far right here, my area, I have 2 variables. I have L and I have W. Well, this perimeter equation can help me get one variable in terms of the other. So let's subtract 2W from both sides, all right, of our perimeter equation. So then we'll get that L is equal to 800 minus 2W. And then I can plug that in to L in my area equation, right? They both represent length. Beautiful. So now we're going to distribute. So I'm going to get 800W minus 2W squared. Okay? So if I have 800 feet of wire, the widest I can be is 400. All right? Because it's a rectangle, so that W, we still have 2W. So assuming that length is 0, the widest it can be is 400. So, right, the smallest it can be is 0. The largest it can be is 400. And let's do it for the length as well, because you could have chosen to solve for W in this perimeter equation and plug W in for this equation and just had L's left over. So L, oh, not W, can be, if W is 0, L can be all 800. Alrighty, so those are endpoints depending on which one you choose. Oops. Area is in terms of W now. So we're going to take the derivative, and that's going to be 800 minus 4W. We're going to set that equal to 0. So we get 4W equals 800, and W equals what? 200. Okay. And now I don't feel like plugging in my endpoints. Say like I forgot to do that and I just like really can't think of my endpoints. I can plug in other W values into A prime and test to see if I'm increasing or decreasing on either side of it to find if it's a max or min. And make sure that it is an extrema. So we're gonna plug in 200 and we're gonna plug in, or sorry, not 200, 300. So those are other W values, and we have A prime. If I plug in 0, I get 800. So that is positive, so we're increasing. If I plug in 300, I'll get 800 minus 1200, which is minus 400. Negative, so I'm decreasing. So bing, 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 bing. W equals 2 yields a max. This is exactly what we want. Yay. All right, so well, now we need to find out what L is. So remember we had L equal to 800 minus 2W. We have that W is 200, so then we have 800 minus 400. So L is 400. Beautiful. So the question asks for the maximum area and its dimension. So I need to plug back into area, length times width. So I can plug in 200 times 400, which gives me 2 times 4 is 8, and then there's 4 zeros. So 1, 2, 3, 4. So that is 800. I think we're given meters. Whoa. Oh. Why does it do that with my M's sometimes? Meters squared. Okay? So maximum area is 80,000 meters squared, which like kind of seems crazy that you can make so many square meters out of just 800 meters. Maximum area is 80 meters squared with the length of 400 meters and width of 200 meters. All right. So if you can on your own, I suggest trying to solve this equation again, or this problem. Using that W equals 800 minus L over 2. So instead of in this perimeter equation we subtracted 2W and we got 800 minus 2W, what if we solve for W? That's my suggestion to you, a little extra practice. Okay, last problem. So, this is another textbook problem. It's an even problem. So, I love this problem. Like I would do with all of these ones, but I really like this problem because after we read it over, you'll notice that there's no numbers. So a window is in the form of a rectangle surmounted by a semicircle. Surmounted means on top of. The rectangle is of clear glass, where the semicircle glass is of tinted glass, as you can see by the purple that I've kind of drawn. Tinted glass that transmits only half as much light per unit area as the clear glass does. So the total perimeter is fixed. Find the proportions of the window that will admit the most light and neglect the thickness of the frame. So we're given that tinted window light is half of what clear window is. Clear window light is. I don't think you're ever supposed to end a sentence with is, but whatever. All right, so what else are we given? Perimeter is fixed. This is really important. Means it's a constant. So even though we're not given like 800 meters like we were last time, the 800 meters helped us find a number, but right here we're only trying to find proportions. So what's that good for is I can just call P P and I don't have to worry about it. I could just treat it as if it was just another number. All right. And we want for proportions. Proportions of the window length and width to maximize the area. All right, cool. So, no, not maximize the area, maximize the light. So notice that we're told that only half as much light per unit area. So that means the amount of light is I can create an equation using the area of the rectangle and the semicircle. So I know that the area of a rectangle is length times width. I know the area of a semicircle is, well, it's going to be half a circle, so 1/2. And area of a circle is pi r squared. So notice that this is our radius, right? Our diameter, 2 times our radius, is our length. So our length of a rectangle is going to be twice our radius. So we can go back to our area of our rectangle and call that 2r times w. Okay. So now we have some equations that we can use to get things in terms of other things. So let's play with perimeter for a little bit first. So my perimeter is going to be this outside of the semicircle, this side, and this side, and this side. Right, we're not including this inside of the perimeter. So it's going to be the perimeter of the semicircle plus 2 times the width plus the length, one length. Kind of like the last one where we only had like 2w plus L. Remember, L is just 2r. And the perimeter of a semicircle is, it's going to be half of, what is it, 2 pi r? And those 2's can cancel out. So we're left with that P equals pi r plus 2w plus 2r. And I like to kind of collect all my variables, so I can make that like 2 plus pi r plus 2w. That's just a personal thing. All right, cool. So now using these two areas, I can make an equation for the light that's being let in. So the rectangle is going to let in all of that light. So all of 2r times w is going to shine through. Plus only half of the light from the area of the tinted part is going to come through. All right. So let me write that, and then I'll rewrite it. Don't worry. So we're going to have 1 times the area of the rectangle plus 1/2 the area of the semicircle. So that is 2rw plus 1/2 times 1/2 pi r squared. We can simplify a little more. 2rw plus 1/4 pi r squared. Okay. Well, I still have L in the terms of W and R. So I need to somehow get, since I have lots of different R's, I want to solve for W in this perimeter equation up here so that I can only have R's in my light equation. So, we have P equals 2 plus pi R plus 2W. This is why collecting all of those R's is kind of useful. So now we're going to subtract 2W. So I have, oh wait, not 2W. Subtract 2 plus pi R. So that I get P minus 2 plus pi, parentheses, R equals 2W. And then we are going to divide by 2. And then, so I get 1/2 P minus 2 minus pi, wait, no, plus, there we go, R equals W. So now I'm going to take this W and plug it in for right up here. So, because I want to get L in the terms of all of one variable. You could have chose to solve for R. I just like to solve for W because it seems a little bit easier since there's only one W versus there's an R here and technically 2 R's right there because it's squared. Alrighty, so we get 2 times R times 1/2 P minus 2 plus pi R plus pi over 4 R squared. So that 2 and that 1/2 is going to cancel out. L equals, I'm going to distribute this R now. So I get P times R minus 2 plus pi R squared. And then pi over 4 R squared hasn't changed. Okay, cool. Awesome. So now all we did right there to go from here to here is I took my known equation. So I know that P is fixed, so P is just a number like 2 or 800, whatever. And I got W in terms of R and P so that I could plug it into L so that I only have R's in my equation. But Mackenzie, there's a P. P is just a number. It's a constant. Just like 2 plus pi is. Just a constant. So now I can take the derivative because I have L all alone with R. So derivative of P R, sweet P, minus 2 plus pi R plus pi over 2 divided by 4 is just 1/2 r, and that's the derivative. Let me make sure that I also had that. Okay, make sure I didn't make a mistake in my notes. So then I'm kind of going to go ahead and I'm going to distribute this too. So I have minus 4 Ooh, no, that's not what I'm going to do. So now I need to get a proportion. So I'm going to set this equal to 0, right? I need to make sure that that's a critical point. And then I also need to plug p back in because it was really important. So we're going to plug p back in. And that's going to equal 2 plus pi r plus 2w minus 2 times 2 plus pi r plus pi over 2 r. So 2 plus pi r minus 2 times 2 plus pi r is going to leave us with 2w is going to stay there, minus 2 plus pi r plus, oh, there we go, 1/2 r. I'm going to distribute this negative and the r, so I have minus 2r minus pi r All right, so I just pulled out r again, and I pulled out the negative. All right, so all I did there was just kind of simplify so I can get kind of all my r's together and all my w's together. So now I'm going to add 2 plus pi over 2r to the other side, so that we get 2 plus pi over 2 r is equal to 2w. All right. And then I can divide by 2. So that I get 1 plus pi over 4 r equal to w. Excuse me. So now I'm going to divide by r. Oh. So I get 1 plus pi over 4 equals w divided by r. And the reason I'm doing that is because I wanted a proportion, right? So I'm not really able to plug in this proportion and be like, oh, that's going to give me this maximum light. I can if I plug in like right here. Whoops. I could plug this in for W into my original light equation all the way up here. If we look at, we didn't really kind of stop and take a note of like how big and small R could be. R kind of doesn't have a end point other than it can't be smaller than 0. But that's why we're only given this proportion. If R is 0, then it's kind of clear that the light that's out of there would be like no window for it to go out. The light would equal 0. So that's why we can kind of stop here with these two proportions. So it's kind of either way you want to write it. So I can write like 1 + 4 pi to 1 if it's asking for radius to width. Oh, it could ask for length to width. So remember that length is 2 times the radius. I would be happy with either of these two answers. All right. So those are 4 different types of optimization problems. This window one is a top 5 favorite. This one is my absolute favorite. Look how beautiful that picture is. Oh, I love it. I really loved optimization problems. So if you guys have any questions about them on your homework, studying for any exams, please let me know. I will love to go over them. I love them so much. I think they're so fun. So that ends today. You guys have an exam tomorrow if you are watching this on time. And good luck. You guys are going to do great, and I'll see you next week.